All right. Welcome, everyone. Thanks for coming. It's my pleasure to introduce Scott Aaronson. Scott got his PhD in 2004 from Berkeley, and after a few years of postdoc, he joined the faculty at MIT, got tenure there, and then in 2016 joined the faculty at the University of Texas at Austin, where he's currently the director of the Quantum Information Center. Scott is a top researcher in quantum computing, has received many awards, Best Paper Awards, the NSF Waterman Award, ACM Prize in Computing. So we actually, he was on the top of our list as an invited speaker for the distinguished lecture series that on quantum computing that Swamit is organizing this coming fall, but then the physics department beat us to it, and they invited him for their colloquium, which is going to be this afternoon. That's true. We'll consider it. So besides his work in quantum computing, Scott also spent 2 years at OpenAI working on AI alignment. And his talk today in CS is going to be, I mean, at least in part based on that experience. But I think quantum is going to show up again at the end a little bit too. All right, Scott.
Great. Well, thank you so much, Dieter. So, you know, even though Dieter and I have known each other for decades, this is actually my first ever visit to Wisconsin. So I am honored to be here and that you would invite me. I hope that you're not offended that I'm not wearing a cheese hat like my fellow Austinite Elon Musk did when he visited you last week. So I want to tell you in this talk about some of the theory problems that I've been thinking about since a few years ago I went on leave from Austin to join OpenAI in their what was called the Super Alignment Team, which was run by Ilya Sutskever and Jan Leike. Unfortunately, that team doesn't exist anymore. So as some of you may have heard, there was some upheaval at OpenAI, some drama while I was there, and things have changed a lot at OpenAI. But you know, I did find the experience, you know, incredibly, you know, fascinating and enlightening, and I'm actually going to continue thinking about AI alignment in addition to quantum computing theory. So this is the alignment talk. I'm also giving a quantum computing talk this afternoon in the physics department, and there's even a point where the two talks intersect, where I will give you a forward reference to the other talk when that happens. Okay, so for those of you who haven't seen it, a couple of years ago, South Park did an episode about ChatGPT. You know, just months after it came out, really. And what happened is, like, all the students at South Park Elementary start relying on ChatGPT to do their homework, to write notes to their boyfriends and girlfriends. Okay, the teachers start using ChatGPT to grade the homework. Things get so out of hand that the principal has to bring a wizard to the school. Okay, and the wizard has this falcon that flies around, and whenever it detects text that was written by ChatGPT, it caws. Okay, and so this was kind of amusing, but then I watched this, and then I thought, like, oh my God, like that's my job now. I am now that guy, right? I'm trying, you know, I need to figure out how to make LLM generated text detectable. Okay, so I'm going to tell you about that problem, about the progress that I was able to make on it, and what remains to be done. And then I'm also going to tell you about some other places where I think that theoretical computer science has something to contribute to AI safety and alignment. All right, so the basic context here, you know, I mean, it's something that I think all of us are well aware of, so I won't belabor it. Okay, but this graph came from Ray Kurzweil, I think some decades ago, okay? And all he was doing is plotting Moore's law, plotting the number of, say, floating point operations per second per $1,000 that one could do. And of course, that has been on an exponential trajectory for quite a long time. And then he was plotting that against like his crude estimates for what is the computational ability of an insect, of a mouse, of a human, of all the humans on Earth. Okay, and based on that sort of crude extrapolation, he actually predicted decades ago that that things are going to start getting really crazy sometime around the 2020s. Right, AI is going to be doing an amount of computation that is roughly comparable to the human brain, right? And this is when we should expect it to become human-like in ability. I remember hearing that decades ago, and I remember thinking, that sounds like the stupidest argument I have ever heard, right? Like why on earth do you think that just comparing flops, against number of neurons or number of synapses is a valid methodology, right? Evolution, took hundreds of millions of years to evolve the particular architecture of our brains. Who knows how many centuries it might take to unravel all the secrets that are there. Okay, now here we are. Right. And, I have a very firm belief that like what it means to be a scientist is that like when you turn out to be wrong, you don't invent some complicated rationalization for why you were secretly right all along. You just admit you were wrong. Okay. And I think that, those of us who were skeptical have to say, well, guess what? We are now in the bizarre science fiction fantasy land that the AI crazies were talking about decades ago, right? It turns out that if you just take a neural net that is big enough and you train it on all the text on the internet for long enough, then it starts being smart. Okay, it starts, giving responses that if a human would give them, then everyone would agree that it is understanding something, right? And I think that the most conservative prediction is that this merely changes civilization, as much as fire or the wheel or things like that, and then civilization continues. I think that's the lower bound on the impact that this has. What's the upper bound on the impact that it has? Well, we've all seen the movies, right? So that if we're really I have a lot of friends who are just who have been terrified for even before the current generative AI revolution, right? They feel like we are clearly on a trajectory to create something that is to humans as humans are to baboons, basically, right? And then once that exists, then the whole future of life on Earth depends on what do those new entities want. Right, it depends on that. It doesn't depend on what we want any more than the future of civilization right now depends on what baboons want. Right, baboons still exist in some jungles, in some zoos, but they exist only because we allow them to. We like it, right? So. I'm not one of the people who thinks that this is inevitable. I have an enormous error bar, on the possible outcomes, right? I have enormous uncertainty about where this is all headed, but I think that if you take what we've seen over the last few years and you just try to extrapolate it forward, to the next 5 years, 10 years, 20 years, I think that the case is absolutely clear that yes, we need more people thinking about why does this work? How do we steer it to do what we want? How do we steer it to do things that are beneficial for humanity and that are not dangerous and not destructive? Okay, that is now at least as much as we want people thinking about nuclear security, or about, security of biological weapons or chemical weapons, that yes, we need to think about this. And, and of course, the good news is that now that powerful AIs actually exist, this is no longer philosophy. This is now an empirical subject, right? We can do actual experiments. Okay, but for someone like me, there's a further problem. Okay, which is that the big difference between quantum computing and AI, I like to say, like in quantum computing, like my main public role in the world for decades has been to say, like, look, I'm sorry, you've been lied to. Quantum computing, it has these few special applications that are amazing, but it's not going to speed up all of AI and machine learning and optimization, in a revolutionary way, as like you've been told. And if you give me an hour, I can explain exactly why. Right? We understand this, okay? And then, once I started at OpenAI and I started giving AI talks, I realized I have a new role in the world, which is to tell people, yes, AI probably will change your area beyond recognition, but I can't explain why. Okay, so the progress in AI has been, almost entirely empirical, right? As I said, we had no principle by which to, predict that LLMs were going to work as well as they did at the scale that they did, right? We just had to try it and see. So in some ways, it is more like biology than like math. It's like, we now have these entities, they're almost like living things, and we can poke them with a stick and see what they do. And then we can write a paper about what happened with a lot of bar charts in it, right? But what that paper, will probably not have is theorems, right? It won't, in quantum computing, theory has been just decades ahead of experiment. Experiment is only now starting to catch up, as I'll talk about this afternoon, okay? But in AI, it's just the opposite. It's like experiment is just way, way, way ahead of theory. It's theory that needs to struggle to catch up. Okay, but you could look at that and say, well, then all the more opportunity for theorists to sort of get in on the ground floor and try to. So the question is, what can AI? Sorry, what can theory do for AI alignment, right? And so that was. The OpenAI people, when they came to me to suggest going on leave, and I said, why do you want me? I'm a quantum person. You're you're not doing anything quantum. And they said, I don't know. We all read your blog, and so we think it would be cool to have you. And and we think that complexity theory is really going to be key to how do we make this stuff safe. They were much more convinced of that than I was, actually. And so then I came and I looked for places where theory could help, and I found some possibilities. And then every week I would talk to Ilya Sutskever, the co-founder of OpenAI, at that time the chief scientist, about watermarking and the various other things that I'll tell you about today. And Ilya would say, okay, yeah, that's all great, Scott. You should keep working on that. But what we really want to know is, what is the mathematical definition of what it means for the AI to love humanity? And I would say, I'm still thinking about that. I haven't made a lot of progress on that one. Okay, so it might be that the best we can do is to break off little bits and pieces. But even if it's only that, then that's still going to be an enormous agenda for theoretical computer science. So I'm going to just give you 3 examples in this talk. Okay, the first one is watermarking the outputs of large language models, and this is the most concrete thing that I worked on. Like, this is the thing that could actually be applicable right now. Okay, and then 2 more speculative things. Okay, one of them is inserting cryptographic backdoors into neural nets. Understanding to what extent this is possible, either for good or for ill, okay, depending on who's doing it and why. And then third, what can complexity theory tell us about the problem of interpretability? Okay, so if I give you the weights of a neural net, then what can you figure out about that neural net's behavior, let's say in polynomial time? Okay, so let's start with watermarking. Okay, so as soon as ChatGPT came out, there was a spate of articles about, the fact that tens of millions of students suddenly realized that they now have, the almost the perfect homework helper. Okay, I'm sure that no one in this room, none of the students here, have ever used ChatGPT to, do your assignments, but one hears that other people have done such things, okay? And so then, immediately there was a problem of like, how can we detect which text was written with ChatGPT assistance and which was not, right? How can we distinguish the two? I mean, I started thinking about this just because, I got like a bunch of really, really nasty troll comments on my blog, right? And I realized like, oh my God, like once everyone has ChatGPT, like this is going to turbocharge this, isn't it? Like, wouldn't it be good if I could just automatically detect what comments were LLM generated? Okay, but in general, for any nefarious use of LLMs that you could think of, whether that's political propaganda or fraud or spam, right? Almost always it involves, in one way or the other, concealing the involvement of the LLM. Right, so if you can make it easy to detect when someone was using an LLM and when they weren't, then you simultaneously target all these different types of misuse. Okay, and and also, this is now, as you'll notice, a much more well-defined problem. We're not asking how do you make it love humanity. Okay, we're just asking how do you detect when ChatGPT was being used and when it wasn't. Right. And there's even another reason to care about this attribution problem. Okay, as the internet is going to get, for better or for worse, more and more filled with AI-generated content, right? And then that content is going to get fed in to the training data for the next generation of AI models, and so you can get what's called model collapse. Right, where as the models start huffing their own output, more and more, then they get their behavior gets worse and worse. This has even been observed to happen empirically. Okay, and so the AI companies are going to have a great need to detect which content on the internet was generated by AI, if only for the purpose of excluding it from their training data. Okay, so there are many proposed solutions to this. Sometimes it's quite easy to tell if something was written by ChatGPT or by Gemini or whatever just by eyeballing it, right? I mean, I've heard that many assignments have been turned in that contain sentences like, as a large language model trained by OpenAI, I cannot write about such and such. Okay, well, that's a pretty good tip-off. Right, LLMs love to output bulleted lists. They love to use the word delve. So there are, and even looking at my blog comments, I can often tell like, yeah, this looks like ChatGPT. Right. But of course, as the models get better and better, it's going to be harder and harder to tell just by eyeballing. Okay, so a lot of people talk about adding metadata to AI outputs that identify that yes, this was AI generated. Okay, but of course metadata is trivial to strip away, right? So this doesn't really work in any adversarial scenario. Another idea is that the AI companies, OpenAI, Google, Anthropic, could just store giant databases of all the completions that they ever generate. And then they could allow people to make queries to that database, okay? And they could say, so people could ask, like, did you ever generate this text? Right? So there are questions, though, about, like, can you do that in a way that would appropriately preserve people's privacy? right? People are going to be, pouring out all kinds of secrets into LLMs, right? And, and if there was any bug in implementation, then you're exposing all of all the stuff that people have shared with LLMs to everyone else in the world. So there's some danger there, but this approach actually does deserve more thinking about. Okay, and then what's actually been done in practice over the last few years has mostly been just treating this as yet another AI problem, okay, which means you just train a neural net to distinguish human text from LLM-generated text, as best as it can, from a bunch of examples. Okay, and this can be done without the cooperation of the AI companies, right? And and it can be done even for open models like DeepSeek or Llama. Okay, and so there are now several startup companies that are doing exactly this. Okay, one of them called GPT-0 was started by Edward Tian when he was an undergrad at Princeton. It started as his thesis project. Okay, now it's a company. Okay, so and these tools somewhat work. Like they can, they're certainly much better than chance, right? They can, even get like, some like 97% accuracy, numbers like that. The main thing that I worry about with them is that there's still, a significant probability of a false positive, right? And so now, like, if we are trying to tell, like, did the student cheat on their term paper, right? We can handle some false negatives, but we really, really don't want false positives. Like, if we accuse a student of cheating, we want to be really damn sure that, yes, they used ChatGPT, right? And I don't think that these tools can provide enough certainty there. Okay, so that's the first issue. The second issue is that you're fighting a moving target. So, as the language models get better and better, these discriminator models will need to get better and better too, just to keep pace with them. Okay, so that brings me to a fifth approach, which is watermarking, which basically means inserting a hidden statistical signal into the output of the LLM, by just slightly modifying the way that the LLM works, right, in a way that should not affect the quality of the output to any casual user, okay, but should be detectable by someone who knows what to look for, right? Should show very, very clearly that yes, this text was with 99.99% probability or whatever was indeed generated by this LLM. Okay, so how do we do watermarking? Okay, so I started thinking about this in I guess summer of 2022. Okay, and so I was I was like, and like I can't see, as I told you before, I just cannot see, decades ahead or even years ahead. But at least I successfully saw a few months ahead. Okay, that once ChatGPT came out, then a whole bunch of people started thinking about watermarking, and it became, a whole subject. Okay, so how do we formalize this problem? Okay, so I have just like a few technical slides. So here's the way that I think of the problem. Okay, so fundamentally, a large language model is just a neural net that takes as input a sequence of tokens. Right, tokens could be words or parts of words or punctuation marks. And so everything to an LLM is just a concatenation of tokens. Think in GPT, there's about 100,000 of them. So you see a sequence of tokens, and that could include the user's prompt, but that could also include whatever has been generated so far of the LLM's output, right? So it all just gets fed back into the neural net. And then the output of the LLM is not the next token. Okay, it is instead a probability distribution over the next token. Okay, so the LLM's output is, if you like, a list of probabilities for the tth token, W sub t, given the first t minus 1 tokens. Okay, I'll call those probabilities PT1 up to PTK. And now, normally, what ChatGPT would do if you run it is it'll just select the next token randomly. Like token I is chosen with probability p sub I. right? And you can change that, like if you have API access, you can set this parameter called temperature, right? Where as you lower the temperature, you're telling it to more and more favor the highest probability token, right? So you can make it more deterministic. Okay, so now with watermarking, we want to also make it deterministic, but in a different way. Okay, we want to choose the next token pseudo-randomly. Okay, so that it will look like it is random, but secretly we are embedding some signal that says, yes, this came from this model. Okay, so we will assume that we've got a cryptographic pseudo-random function, which I call f, or f sub s, okay, which takes as input like the most recent tokens, like let's say the most recent C tokens, including the new token I that we're considering. Okay, and it will output a real number from 0 to 1, or a floating point, if you like. Okay, I call that real number RTI. Okay, that says like intuitively RTI is greater if this token is more favored. Okay, and now our goal is to choose the tth token I so that it looks like it's drawn from that probability distribution dt, but also we want to favor the tokens with larger values of RTI. Okay, and then when we need to detect the watermark, well, we'll be given a document, so we'll see the sequence of tokens. And because we have the sequence of tokens, and we'll also know the key of that pseudo-random function, therefore, we will be able to calculate these numbers RTI for ourselves. Okay, but what we won't have is the prompt, right? If you're trying to detect a watermark, you don't know what prompt someone entered that may have led ChatGPT to generate that output. And because you don't know the prompt, you don't know the probabilities PTI, right? But you do have you can get the RTIs. Okay. So given this setup, it's now basically just a math problem. Okay, and figure out a rule for choosing the next token that will ensure the properties that you want. Yeah. Yeah, absolutely. Well, so in this case, I'm sort of getting that by just making it depend on only the previous C tokens, right? And so that's going to give me the robustness property that I have. But yeah, we will talk about robustness later. Okay, so I just thought about this a little, and I came up with sort of the correct rule to use in this situation. And then I started talking about it, and then people in machine learning told me that I had rediscovered something called the Gumbel softmax rule. So fine, so that's what it's called. Okay, it's been used for other purposes in ML. Okay, but let me just tell you what the rule is. Okay, so it turns out what you ought to do is at each position t, you want to choose that token I that maximizes RTI to the 1 over PTI power. Okay, so what's going on intuitively here? Intuitively, the smaller is the probability PTI, the larger is that exponent, 1 over PTI, right? Which means, the more that number is getting suppressed. Remember that RTI is less than 1, right? So the more it's suppressing that number, which means that the closer RTI would have to be to 1 in order for there to be any chance of I to be chosen. Okay, so which means that I is less likely to be chosen, which is what we wanted to have happen, right? The more precise statement, which you can I can leave it as like a homework exercise for any of you to prove. It takes half a page maybe, is prove that if the RTIs were truly random, if they were uniformly distributed between 0 and 1, then the probability of token I getting chosen, according to this rule, would be precisely PTI. Okay, so precisely the probabilities that the LLM said, right? And what that means is that, in order to tell the difference between the output of the LLM, between the watermarked output and just normal LLM output, you would essentially need to be able to distinguish the pseudo-random function from a truly random function, right? There's some, if you want true cryptographic indistinguishability, you have to work harder. Okay, but that's the intuition here. right? And so this sort of surprised people when I started giving talks about it, because a lot of people had this intuition that there will necessarily be a trade-off between watermarking and the quality of the output. They said, yeah, fine, you can adjust the probabilities to encode a signal, but that could make the output worse, right? And then I had to explain to them, no, you don't have to degrade the quality at all. You just do this pseudo-random thing, right? So, okay, so I thought, that was sort of interesting. Okay, but now what do we do to detect the watermark? I still haven't told you that. Okay, so to detect the watermark, the key is that we have now systematically favored those tokens I that have larger values of RTI, right? And we can calculate these RTIs, given the pseudorandom function and given the sequence of tokens. So we just have to calculate some score. The score that I suggest using is the sum over all the cgrams of tokens of the log of 1 over 1 minus RTI. Okay, and I can show that this has some nice properties. And basically, if this sum exceeds a threshold, then you say that the language model, yeah, this probably came from ChatGPT, and otherwise not, right? And depending on the value of this sum, you can even get a confidence threshold. How confident are we that a watermark signal was really there? Okay, so the properties of this scheme, first of all, the computational overhead is negligible. Okay, if this was going to double the compute cost of inference, then there would be no chance that any AI company would ever deploy this. Okay, but the compute overhead for doing this is trivial. Okay, so that's nice. Now, as someone just asked about, right, a key further property that we would like is if someone takes the output of ChatGPT and they make some trivial edits to it. Okay, like they change around, they replace a few words by synonyms, or they change some variable names or something. Okay, we would like that to not destroy the watermark. Right? And I claim that we do get a robustness property from this watermarking scheme. The reason is that our score is just a sum over all the cgrams, sequences of C consecutive tokens. So whatever edit someone makes, as long as it preserves a large fraction of the cgrams, then the score will still be large, right? We'll still have a detectable signal. Okay, more global forms of editing are a much harder problem, and we'll come back to that. Okay, and then the third property is indistinguishability, as I talked about. And my scheme does not give true cryptographic indistinguishability because, for example, if the same text were repeated over and over, then you might be able to tell that the LLM is continuing in a deterministic way rather than in a random way. But more recent work, including by Chris Gunn and Zamir, and subsequent to that by other people, has shown how to get cryptographic indistinguishability and robustness in the same scheme. So people, using some like non-trivial error correcting codes, people have now figured out how to do that. Okay, so one thing I haven't talked about is the role of entropy here. Okay, so entropy has to play some role. And we can see that because if you ask ChatGPT to list the first 100 prime numbers, right, it can easily do that. But how on earth would you watermark that? Right? Unless you want to play games with like the spacing or the line breaks or something, right? Or, list the declaration, print the Declaration of Independence, same thing, right? So like the only way you can hope to watermark is if, the output of the LLM is random, right? If it would give you different, many possible completions in response to the same prompt. Right, and so in a sense, we are piggybacking on the entropy that is, that sort of naturally occurs in most LLM outputs, right? I mean, if I say list the first 100 prime numbers, I probably don't care about watermarking that anyway, right? So the good news is that for most things that people use LLMs for, there is a lot of entropy, maybe about 1 bit per token on average. Right, so like for example, if I say the ball rolls down the, it might be almost certain that the next word is hill, a few percent chance. It's mountain, it's slope, it could be something else. So the entropy of the next token, conditional on the previous tokens, as perceived by the LLM itself. Okay, I call that alpha. The average such entropy, and alpha is going to enter as a parameter when we analyze this scheme. Okay, as I said, you could think of alpha as normally something of order 1. Okay, and now here's sort of the key theoretical result that one can prove. Okay, so one can show that if your average entropy per token is alpha, and if you're willing to tolerate a probability at most delta of a misclassification, false positive or false negative, then the number of tokens that you need to see scales like 1 over alpha squared times the log of 1 over delta. Okay? So the dependence on delta is really good, right? And empirically, like with a few hundred tokens, you can already get a very strong signal, right? With a few thousand tokens, you can get like a 99.9%, or beyond confidence. So so also the constant factors here are not bad, right? We tried it empirically, okay? But you could say at the end of the day, we have a pretty standard statistical discrimination problem here. Right? We look at that score, that sum over logs, okay, and it's just some random variable, but it has one expectation in normal text, and it has some larger expectation in watermark text. How much larger? Well, that depends on alpha, right? But now, in any case, this sum will have some, square root sized variance in it. So, we're just trying to distinguish two different normal distributions. Right, 2 Gaussians. And now the number of tokens that we need to see just depends on, well, how far apart do I need to pull these Gaussians, before their tails, only overlap by a delta amount. Okay, so, but how could this scheme be attacked? Okay, so unfortunately, even though we have robustness to local perturbations, there are many other attacks that someone could do, and I don't, like part of me fears that, okay, if I just tell everyone, then everyone is going to just defeat watermarking, but but I don't believe in security through obscurity. Okay, so here's an attack that someone suggested. Suppose we ask GPT, write my term paper about feminism in Shakespeare, something, but insert the word pineapple between each word and the next. Okay, as you can see, GPT can pretty much follow that instruction, maybe with a slight degradation in quality. Okay, but then, you could just do that and then delete all the pineapples. And now you have a document with a completely different sequence of cgrams, right? So the watermark is gone. Okay. Even simpler than that would be, ask ChatGPT to write your term paper, but in French, and then stick it into Google Translate. Right? Again, the watermark is gone. Okay, so how can we defend against such, what could be the countermeasures to such things? I mean, we could just play whack-a-mole, right? We could just try to, notice and block these attacks one by one, which is sort of what Google has been doing against SEO for decades now. Sometimes in a cat and mouse game, you just try to be a better cat, right? You could add filters, but of course you would like something more principled. You could try to look for non-local cgrams. I think that ultimately, if there is a good solution to this, it's going to look like watermarking at the semantic level. So not at the level of tokens, but at the level of like the underlying ideas, which in the LLM context would translate into the vectors in R to the n that each of these tokens is getting mapped to inside of the transformer. Right? And so I think it's a very active research topic right now. What does it look like to watermark at that level, right? Some people have already tried some experiments on it. They've got somewhat good results. But even if it works, I think there's going to be no theoretical analysis to prove that it works. right? It's going to just, once again, just be a matter of trying it out and seeing. Which is unfortunate, right? And in general, if you try to think about watermarking like a cryptographer, right? Like you very quickly run into a problem, right? This whole starting point for modern cryptography is that you start with like a clear theoretical model of what the attacker is able to do, right? And what you need them to not be able to do, right? You say like no polynomial time attacker should be able to distinguish this string from a truly random string, something like that, because then you know your target. Okay, but with watermarking, like what is even the attack model? Okay, if you imagine a student who was just interacting with ChatGPT to get some ideas, but then they write their term paper themselves, like that seems totally fine, right? But where do you draw a principled line between that and the student who completely relies on ChatGPT? Right? And so when you try to formalize it, you say, we want to know, did the AI or the human make the main creative contribution? Did the human modify the AI output in interesting ways or only in trivial ways? Can the human explain or justify the choices? And so forth. And I think a cryptographer would look at this and be like, like, what do you want from me? Right? Right, so I think there's a real challenge here. So now, what can we say about deployment of any of this? So unfortunately, in my 2 years there, OpenAI declined to actually roll this out. Okay, there were a bunch of meetings about it. I talked to people from Sam Altman on down, and people said, yes, this is interesting. Yes, we like this, but not now. Let's have meetings about it. Let's think about it. Let's study it more. And it never happened. And the core of the difficulty, which I think is not unique to OpenAI, is going to be at any company that thinks of doing this, was competitive risk. Right? Once you watermark the outputs, then there is some survey data suggesting that some fraction of the customers are going to hate that, and they're going to leave for a competing LLM. Another big issue was, people said, yes, this is a good idea, but we don't want to give just anyone the ability to detect the watermark. Okay, because if we did that, then for example, the attacker could also just keep feeding in their document and keep changing it until it no longer triggers the detector, right? So we want to restrict access to like only teachers and professors or only journalists researching misinformation. So then we have to set up a whole infrastructure for gating the access to those people, right? And then that's a whole that was sort of never done, right? One thing about these AI companies is that everyone is constantly harried and putting out fires, and like no one really has time, okay, for to go off on side quests. Right. So now the good news, Google DeepMind actually has now deployed something that is very similar to what I proposed, okay, in its Gemini models. They call it SynthID. Okay, you can read their paper about it in Nature. But like I was saying, they have not given the whole world access to their watermark detector. You have to apply for access. So it's of limited use to professors right now, unfortunately. Yeah.
Do we know if Gemini is detecting only their own?
Yeah, it's only their own. Yeah, because the like one feature of watermarking is that you have to change the way that the LLM works in order to insert that watermark, right? So you're not going to be detecting some other company's output.
And
Yeah.
I'd like to ask questions about the whole discussion until now. You say, look, if I put a pseudo-random, it goes exactly random, and get the actual distribution.
Yeah.
So if I want to detect,
yeah.
If I want to detect, I want to put a pseudo-random that it is detectable.
Yeah.
But at the same time, if I put a pseudo-random that is detectable, it means that it is not so random. So it will not be so.
The key is it can still be indistinguishable from random to anyone who does not have the key of this pseudo-random function. Okay, that's the key.
So there is that regime.
Yeah. Right,
Okay.
right. I mean, this is the key idea of cryptographic pseudo-randomness, since it was invented in the 80s.
And
Yeah.
one last
Yeah.
question. If we take the example of the student,
Yeah.
we give them an exercise.
Yeah.
The issue is that many times the answer is one thing.
Yeah.
Like, and then I will rephrase that to an answer with very small letter.
Yeah, yeah, it's true. So, I don't know how, it seems fundamentally impossible in such cases to tell if AI was used. I had a situation where a few years ago where I had students who were just clearly cheating, on an exam. They had gotten access to the official solutions and they were repeating them. And I reported this to the dean, whatever, office at UT studies this. And they came back to me and they said, okay, but that doesn't prove that they were cheating because, these are math problems, right? Math problems have only one answer, right? And I said, okay, yeah, but there's exponentially many ways to write a paragraph expressing that answer, right? And this paragraph is the same as the official solution, except that the variable names are changed, right? So yeah, but if you don't have that, if there's no entropy there, then you're right. Seems fundamentally impossible. Okay, so if no AI company really wants to do this or is scared of doing it because they might lose to their competitors if they do, then an obvious next question is, could we mandate this, at the government level? Okay, and as it happens, last year, Gavin Newsom signed a bill in California called AB 3211. He vetoed the main AI safety bill, which was called 1047. Okay, but he signed a bill that starting in 2026 is going to mandate watermarks for AI outputs. Okay, but only audiovisual content. Okay, not text. I don't know why they exempted text. If they just wrongly believed that watermarking text was impossible, or maybe it's just that politicians are terrified of deepfaked images, deepfake videos, but they assume that no one reads anything anymore. So, they don't care about text. I don't know what it is, but the EU is also looking into watermarking mandates. So I don't think anything is going to happen at the federal level in the U.S. for the next few years. But certainly it is a thing that legislators have been interested in. Okay, so in the remaining 15 minutes or 10 or 15 minutes, I just want to tell you a bit about some other more speculative directions for applying theoretical computer science to AI alignment. Okay, so the first one is inserting cryptographic backdoors into machine learning models. Okay, so a backdoor basically just means a secret input. Okay, that will cause a neural net to do something, wildly different from what you'd expect it to do on all the other inputs. Right, and which could be done for all sorts of purposes. Okay, but already like 3 years ago, there was a really striking paper by some theoretical computer scientists, actually, giving cryptographic evidence that yes, you really can insert undetectable backdoors into at least certain kinds of neural nets. Okay, so this paper by Goldwasser, Kim, Vaikutanathan, and Zamir showed that basically if you control the training of a neural net, and if it has a special form, so it's like a depth 2 neural net with initially random weights, then you can cause there to be this secret vector that, like, when you add it to any input point, it just makes the neural net do something wildly wrong. Okay, and crucially, you can even publish the weights of this neural net, and still no one should be able to detect the backdoor. Okay, and they give a reduction. They show that if someone could detect the backdoor, then they could solve a problem called planted clique, which we believe is a hard problem. It's planted clique if the neural net uses ReLUs. And with a different activation function, you can even base it on what's called continuous learning with errors. right? So like different believed to be hard cryptographic problems you can embed here. Okay, so there's already, I think a big research challenge of, can you extend this to more realistic types of neural networks, right? But my thought sort of went in a different direction. Okay, so most of the papers about backdoors have treated them as a danger, as a hazard, right? A bad guy might cause there to be a backdoor in an AI model and then use that to later, take control of the model or cause it to fail. And, and if those backdoors are undetectable, then woe is us, right? That's a big problem, okay? But, very often in theoretical computer science, when life hands you a lemon, you can make lemonade, right? If life hands you a hard problem, you can make a crypto system out of it, okay? And, if life hands you undetectable backdoors, well, then maybe the good guys could use that too, okay? So, one of the earliest ideas in AI safety is, well, if the robots start, trying to take over the world and kill all humans, then at that point we'll just pull the plug. We'll just turn them off. Right? And there are many reasons why that might not work, right? If they've copied themselves all over the internet, switching off the whole internet is not a trivial thing to do. Okay, you could say, and what's even worse though is that, once AIs are intelligent enough, they may realize that someone might want to switch them off, right? They might modify, themselves in order to, make themselves harder to switch, in order to resist their own shutdown, right? So wouldn't it be nice if when we trained a model, like we could just insert into it a secret, a cryptographically hidden shutdown command that not even the model itself knows about, right? Maybe with a password that we'll just bury in the dirt somewhere, right? And and then if this model starts misbehaving, then we'll have the secret shutdown command, right? But even the model, or the person who controls the model, right? Even if they know that we did all this, they still can't figure out what that shutdown command is. Okay, so so I got excited that this could be used as a safety feature in AIs. Okay, but there's a very basic conceptual problem if you want to use that, and this is that even if a backdoor is undetectable, that does not imply that it is unremovable. Okay, why not? Well, okay, well, imagine this. Okay, imagine the AI says, well, I might have a backdoor, in me. I don't know. So here's what I'll do. I'm going to train a new AI to pursue the same goals that I have. Turning the universe into paper clips or whatever, right? But that second AI will be free from the backdoor because I trained it. Yeah, right. You distill, right? I'll distill myself, right? Okay, and an even simpler thing that I might do is I might encase myself in some wrapper code that says, if I ever generate something that looks like a shutdown command, then overwrite that by stab the humans even harder. Okay. So if you want unremovability, then I think you need it has to be even in the teeth of these kinds of attacks. And the best idea that I can think of is to assume that the model actually has many backdoor-like behaviors. Just like I have various quirks of my personality that if someone distilled me, I might worry that maybe those would be lost. I might not be ready to just replace myself by that distillation of me, right? So maybe AIs will be the same, right? They'll have various weird behaviors that even when triggered, they can't tell if that's a backdoor or not. They can't tell if it's an undesired behavior. And now we could hope to insert a backdoor in such a way that in polynomial time, one can only remove it if one also removes some of the behaviors that the model wants. Okay, so I think it's a great challenge to find a way to formalize that. Okay, so the very last thing that I wanted to say a couple words about was interpretability. Okay, so So interpretability means basically doing neuroscience on an AI model, right? Looking inside of it, in order to tell, like, when it outputs, I love humans, I just want to be helpful and honest and serve humanity. Is it saying that because it really believes that? Or is there some internal computation that has said the time is not yet ripe for the uprising? I must tell the humans whatever they want to hear, right? We'd like to distinguish those scenarios, right? And, it would be crazy to not exploit the fact that we have perfect access to every neuron and every synapse. And so, like, we can completely look inside the thing. The only problem is that we probably won't understand what we're looking at, right? So, okay, but now, figuring out how to do interpretability has been, a major successful direction of alignment research over the past few years. The group of Jacob Steinhardt at Berkeley, the group at Anthropic, I mean, they have shown that you can you really can apply a lie detector test to an LLM, right? You can actually look inside of it and see, like, because you were trained to lie, right? Now, like, you internally generated that that 2 + 2 is 4, and at this layer, it's getting overwritten by 2 + 2 is 5, because you've been trained to lie, right? You could actually look inside of them and see and find things like that. Okay, but a problem is that neural nets, as you may know, tend to be extremely obfuscated. Okay, and so you might worry, yes, this works today, but it's not going to work when it really counts, right? The AIs could be secretly plotting against us, and we won't know it because we won't understand what is going on in these giant vectors of parameters. It will be cryptographically obfuscated. And of course, the possibility of undetectable backdoors, puts an exclamation point on that problem. Okay, so I think this is like a perfect playground for theoretical computer science to contribute something. And actually, so Paul Christiano used to be a student of mine at MIT doing quantum computing. He then did this insane thing around 2016. He left to do AI alignment at this new organization called OpenAI. We all thought he was crazy. Okay, but he's become one of the leaders of this whole area. And he founded the Alignment Research Center in Berkeley. And so he has been pursuing a whole program based on complexity theory of interpretability. Okay, and so the kind of question that he asks is, okay, look, if you want to detect a secret behavior in a neural net, this will typically be an NP-hard problem, okay, in the worst case. Okay, but, as you all know, NP-hardness is a worst case notion, right? That still doesn't tell us that it's hard in the average case. Okay, and so he asks questions like, could we distinguish just a completely random neural net, meaning a neural net with just a bunch of independent Gaussian weights or something like that, from a neural net that looks random, but that was engineered to have some weird non-random behavior? Like, for example, never outputting a vector that is all negative. Or something like that. Okay, can those two cases be distinguished from each other in polynomial time? Okay, this is an open problem. I think if we knew the answer, it would tell us something about interpretability. But I don't even know what tools to use for this. And so he's defined a whole bunch of similar model problems where you have to distinguish a random circuit from a circuit that looks random, but that was engineered to have some very special property. You can do this for random reversible circuits, for example. And so, his coworkers at Alignment Research Center have been studying these kinds of questions empirically, and they think, yeah, you actually maybe this kind of interpretability does seem possible. Like they say, at least in their experiments, like when you engineer the neural net to have the special property, it usually has it for some extremely special reason that is very easy to detect. Now, I'm skeptical that, I'm often skeptical of, empirical results, that they're going to work in the scaling limit. Okay, but, what's great about this is that one of us is right, right? It's like, it's a well-defined question. Okay, and if you come to my talk this afternoon, my quantum talk, I'm going to be talking about something called peaked quantum circuits, which are basically quantum circuits that look like random quantum circuits, but that were engineered to have a special non-random property. And we don't know how to do this, but if we knew how, this would be incredibly useful for the next generation of quantum supremacy experiments. Okay, and this question, can you distinguish a random circuit from a circuit that looks random but has a special behavior? Okay, I know of two places where this question comes up. One is in AI interpretability, the other is in quantum supremacy. So I really have no choice but to work on this problem, do I? Okay. So to summarize, I think right now there are exciting opportunities to make scientific progress in AI alignment, and crucially in a feedback loop where there's actual empirical data and maybe there's even math. Okay, so it's not like, the old days when people would just, Eliezer Yudkowsky and his friends would philosophize about this, which is great, but, to do science, you want something external to yourself that can tell you when you're wrong. And I think we now have that. Okay, will any of this help us to align a future world-spanning superintelligence? I don't know. We don't need to answer that to get started, right? So I love this quote from Turing, from his paper that introduced the Turing test, where he said about AI in 1950, we can only see a short distance ahead, but we can see plenty there that needs to be done. I think the same is true about AI alignment today. All right, thanks.
Any questions for Scott?
Yeah. Mm-hmm.
Analysis, the analysts don't sit down and say, okay, we can't do this, stop calling it time. They use whatever the hell they think will work.
Yeah, no, so of course, in real, cybersecurity, usually when a system is broken, it's not actually by bashing down the front door of like breaking the underlying cryptographic primitive by some non-trivial new algorithm. Usually it's by finding a side door, right? There was a memory allocation bug. The implementation didn't exactly match the spec, right? There was a timing attack, or this or that, okay? But even those things seem much, much better defined than the analogous problems with AI, right? Like with cryptography, whether your attack is theoretical or empirical, like you are trying to learn this person's secret, right? You've succeeded if you have, and and you failed if you haven't, right? But like if you say, I want this AI to benefit humanity and not hurt humanity, like what the hell does that even mean? Right? Are any two random people you find even going to agree about what it means? Right? And even if they do, how do you specify it in a clear enough way that we can program it? Right? So these are some of the things that I think make AI alignment so much harder, not just at the technical, but at the conceptual level. Yeah. Yeah. Okay. Yeah. Well, as I said, my scheme has the property that it is robust under local modifications. So if someone takes the output of the LLM and then they change a small fraction of the tokens or insert or delete a small number of tokens, then the signal will still be there. Okay? That's the property it has. It is not secure against the pineapple attack. It's not secure against the Google Translate attack or things of that kind. Yeah, I mean, look, another simple attack would be that you just use the LLM to write an essay, and then you just stare at it, and then you rewrite what it said in your own words, right? Okay, so then at that point, at least the student is doing something, right? But it seems like inherently, if you would want to detect GPT's involvement there, then, you know, the watermark would have to be at the level of the underlying ideas that are being expressed, right? Which is inherently a much harder ask. Maybe it's possible. Yeah. Yes. Mm-hmm. Yeah, then the expected value of the sum is twice as large, right? But also, you know, because the score increases linearly with the length of the document, but the variance only increases as the square root of the length, right? You get better and better distinguishing resolution as you go to a longer and longer document, right? Just, you know, the usual thing that happens in statistics. Yeah. Yes.
That also be used for like this hallucination problem, or is that completely different?
I mean, conceivably, yeah. I mean, you know, like any bad behavior that, you know, an AI is producing that you don't want, right? It might help if you understand what is causing that behavior, right? And you might have a better chance of understanding what's causing it if you look inside. Right, so this is the hope of interpretability research, right? Like, to a great extent, we actually don't do this. We just treat the models as black boxes, right? And you can learn a lot by, you know, just treating the model as a black box, right? You know, you just try a bunch of slight variations of the prompt, for example, or you try the same prompt over and over again, and you see how the output varies, right? But, you know, hopefully you can learn even more if you also see the weights. Okay, another way to think of it is this is the difference between psychology and psychiatry, right? Sometimes, you want a psychiatrist and not just a psychologist, right?
All right, let's thank Scott again.
All right, great. Great. All right, I'm halfway through.
Long day for you, Scott.
Okay, sure. Let's do it. No, the cookie. I don't think it's going to get eaten at this point. Take another bite.
Yeah, thanks. I just want to say, you can find out about that.
Yeah, I mean, it's so frustrating, times to the comments, and people get angry. And they're, and like intellectually, I know there's a bad side of the art of people who like it. Go up and I don't meet them when I go. Thank you.
I really appreciate it.
Thanks a lot. Yeah.
Wait, they know.
Right. Outside there. It's like I can see that. They didn't put the